In this video, we'll see how to analyze our protein melting data to determine which, if any, of our various test conditions lead to either an increase or decrease in the stability of our protein. To get the analysis started, simply click the Analyze button. The first thing I'll do is simplify the look for a moment by turning off some of the graph features. What we're left with are two graphs of essentially the same melt data. The top one showing straight fluorescence as it changed over the course of our melting profile, and on the bottom, the first derivative of that data. If we go to Show in Plot, Derivative TM, we see the melting temperature for this sample based on the inflection point of the curve. And by selecting various samples down below, we can either view this data for individual wells, or we can even highlight multiple samples at once. In any event, the melting temperatures for each sample are also presented here under the column TM, D of course meaning derivative. Another way to calculate TMs is to use a Boltzmann fit. When we choose that option instead of derivative, the software looks for the region of each curve in which fluorescence increases. This becomes known as a region of analysis, which we can see is defined by these gray lines. Next, the Boltzmann algorithm does a sigmoidal fit to each line, like this. The inflection point of that line is considered the melting temperature of the line. Now, notice that when I choose to show the derivative-based calculation of TM, it's different from the Boltzmann TM. This is to be expected. As long as we're consistent across the samples we're comparing, the choice, especially for single peak melting profiles, might not be so critical. And by the way, we do have the option of manually setting regions of analysis on a per well basis. To do this, I select the well to adjust, click this plus symbol, drag out a new region of analysis, make any fine adjustments that I want, and hit Analyze. To go back to the auto setting, I simply select one of the two blue lines, hit the minus sign, and again, Analyze. I have the option to color my curves differently, which is a very quick and powerful way of picking out patterns. For example, say I wanted to know which parameter has a bigger effect on melting temperature, buffer or salt concentration. I can figure this out really quickly. I'll start by selecting all of my wells so every curve shows up. I'll also deselect everything under here to clean up the graph. Now what I'll do is say color by salt. And when I do that, I see a lot of mixing of colors, suggesting that salt concentration isn't having an effect on TM that's easy to see at first glance. Now I'll color my curves by buffer instead. When I do that, suddenly I see a huge correlation between buffer and melting temperature. And just like that, my question is answered. Let's have a look at replicate results under the Setup menu. Here, all four of our identical replicates are lumped together in a highly graphical format. The data are presented hierarchically, as shown here on the right. Now we can change the ordering of that hierarchy by clicking the Condition Hierarchy button and rearranging the order of the various parameters. I'm going to draw a box around the region containing these geometrical figures to get a closer look. Now, to understand what we're looking at, let's click this button so we see the graph legend. The red dots are just the identical replicates for a single set of conditions. The green lines with the heads on top define the median value of our identical replicates, while the gray lines in the middle are the mean values. These larger diamond shapes define the spread of our replicates, so for cases where the diamond is big, our replicates probably weren't as tight as they should have been, possibly due to pipetting inconsistencies or to a problem with the sample itself. There are no major outliers on this plate, but I'll use our biggest triangle as an example of how to omit wells that are causing problems with precision. There are three replicates that are fairly tight, one that's outlying over to the right. First, I need to identify which sample this is. To do that, I click somewhere in my sample list, then use either my up or down arrow until the triangle for the sample of interest is highlighted in blue. Once we find it, we can look over to the right and see the individual TMs for the replicates, and even omit the outlying replicate to tighten up the data. Now, when we hit the Analysis button, and we zoom back in, we see that the outlying point is no longer being considered. And of course, we can always re-include that data point later on. Right now, our data are being plotted as Boltzmann TMs. This view certainly shows us that our samples are clustering based on buffer type, something we saw a moment ago when we colored samples differently. But let's say we want to isolate samples that differ from the reference sample in terms of delta TM, based on a defined cutoff. I'm going to click on Analysis Settings. Here, where it says Positive Hit Settings, we can define a minimal delta TM cutoff, such that only samples that melt a certain number of degrees above or below the reference sample are labeled as positive hits during the analysis. I'll just change these values to 3. Now, when we apply and say OK, and we switch our plot to one of the delta TM views, this blue box appears. Now, what the box does is isolate samples that meet the threshold cutoff that we just set a moment ago. Here's our reference sample in red. Notice its value on the x-axis is 0. Any sample that is at least 3 degrees higher in TM will appear inside a blue box. Now, these samples are now designated as positive hits, and we can also see when we go back down to the results, the samples are tagged in this column as positives. When we're ready to export the data, we simply go back over to the workflow menu and click Export. Here, we can really customize what data we export, including either the raw data in several different formats or the analyzed data. In the second instance, we can export individual wells or replicate data. Also, we can deselect any columns that we don't care about in order to clean up the data. Finally, we can choose an export format, either .txt or .csv, before hitting the export button. One last thing I want to touch on is a very unique ability of the software, namely its handling of data with multiple peaks. So sometimes the proteins we want to analyze are multiphasic, meaning they have complex melting patterns that create more than one peak. Most analysis software has trouble with this kind of data, but not protein thermal shift software. At first, the software autocalls only a single peak. But if I go down here to Auto Analysis Options and choose Auto Multiple TM, and then go back up to the top and hit Analyze, the software is now calling 5 different peaks, as well as calculating a derivative TM for each. In fact, the software even allows you to manually assign where the multiple regions of analysis should be, if, say, you want to focus in on a particular temperature range. Now, once we have our peaks defined, we can go down to the results pane and compare the TMs for individual peaks. Well, let's say we have an experiment in which certain test conditions lead to our protein melting as a single phase, while a different set of test conditions lead to our protein melting in multi-phases, all in the same experiment. Well, how do we calculate a delta TM when the number of peaks between samples doesn't match? Well, protein thermal shift software actually helps us do this. Let's go back to Auto Analysis Options and choose Auto Single TM. Next, we'll go back up to Show and Plot and make sure that both Boltzmann TM and Boltzmann Fit are selected. For the wells in which we have multiple peaks, we see a green line for the Boltzmann Fit in the fluorescence plot that effectively represents an average TM of the multiple peaks, regardless of how many peaks that sample contains. If we also select a well that contains only a single peak with a single TM, the software can now easily calculate delta TM values across these otherwise quite different samples. And that's really all there is to the protein thermal shift assay. It's a versatile addition to any protein lab, especially those with the need to perform high-throughput screening. Simple reaction setups, fast run times, and straightforward analysis workflows, all for pennies per reaction. And best of all, the protein thermal shift assay works on Applied Biosystems real-time PCR instrumentation, machines that can just as easily perform quantitative gene expression studies, protein expression, genotyping, and a multitude of other applications in low, medium, or high-throughput formats. If you'd like more information on the protein thermal shift assay or on Life Technologies' wide array of real-time instruments, please don't hesitate to contact your local sales rep or application specialist. Until next time, so long.